A traditional robotics pipeline consists of multiple sensors, such as LiDAR, images, depth cameras, and IMUs. And all this system information is fed into a sequence of modules, such as mapping, localization, motion planning, and final level controls. This traditional approach requires a lot of human expertise and prior knowledge in defining the exact sequence of modules, their inputs and outputs. Our approach, in contrast, uses a single common shared representation for multiple downstream tasks. Our key idea is that despite being different, all these tasks share commonalities in their feature space. And by using PACT, we can still take advantage of the modularity of robotics while using the latest advancements in representation learning. To train this representation, we use a autoregressive causal transformer that tries to predict the next states and actions that the robot should see in its dataset sequences. This pretraining scheme ensures that the representation learned by the network has some notion of environment dynamics and also of the control policy of the agent. We can then use the same representation towards multiple downstream tasks, such as localization and mapping. And we do this by modifying the original tokens learned by the pretrained network towards these multiple downstream tasks with new fine-tuning heads. To pre-train this representation, we collected medias and perception action pairs for two types of robots. Here you can see a video of the MuSHR platform, where we use the MPC controller and a trajectory library to collect several hours of navigation data in realistic hallway environments that were actually taken from a real-life office building. The second environment we tested was habitat, where differently than MuSHR, we deal with a discrete set of actions, and also with RGB data information as the perception input. Similarly to how a large language model like GPT-3 operates, this autoregressively trained causal transformer learns to output reasonable sequences of actions for a robot. Here you can see that even though this robot has no notion of go state, it's just trying to navigate safely through the hallways, taking reasonable actions. We can also view this pre-trained transformer as a generative model for robotics, where by using different prompting sequences, we will see different output distribution of states and actions in the robot. After pre-training, we can fine-tune the PACT representations towards multiple downstream tasks by coupling different downstream task decoders. Here you can see three examples of a local mapping network, real-world navigation examples, and localization. We also have examples for the habitat environment, where we use RGB information and a discrete set of actions to train a representation and then fine-tune it towards local mapping and localization. We also deploy the pre-trained policy in the real vehicle, where it's able to overcome the sim-to-real gap in terms of model dynamics, actuator and processing delays, and noise information in the sensors. We provide another example of real-world deployment from the perspective of the vehicle. On the left, we have the LiDAR projection, which is the actual perception input for the model, and on the right, we have the active RGB camera inputs, which is not an input to the model, but it's only there for visualization.